Hello everyone, today I want to introduce linear systems for lecture 3. So the first one, we want to analyze the continuous systems. In linear systems, we may analyze two systems. One is continuous systems, one is discrete system. As you can imagine, in mathematical, the continuous mean when you draw the characteristic 1, 2, 3, they will continue. But for discrete, they will also only like this, right? Only 1 point decrease. Okay. So I will introduce the basic concepts like state space I/O relationship. We will introduce first, and next we will introduce how to express it in canonical form. The third one I will express how to express it in observed form. Okay. So this is our lecture 3's content. Actually, for lecture 4, we will introduce discrete time. As for discrete time, you will also learn about the same concepts like the state space equations in discrete system, the canonical form and observed form in discrete system. Also, you will see about the nonlinear system. Nonlinear system, we will always first make it linearization. After we do the linearization, we can analyze the other thing. So in the next contact, you will see that lecture 4 and lecture 5, we will introduce linearization. For lecture 7, we will introduce a new theorem, Canonical theorem. Also the recover meaning on lecture 8. Do not feel that difficult. A linear system is a connection subject between calculus, mathematics, and control system. Linear system will help us more familiar, more easy to analyze the control system. So let's see lecture 3 for continuous system, the space-based I/O relationships. First, for the whole lecture, we will always use mass spring damper because it would be the most commonly system for us in our analysis. These systems will include mass, spring, and damper dot coefficient. In dynamic, you may have learned the expression for mass spring damper formula. After analyzing, we can get the most simplest, the most common formula is this one. In this subject, if you do not know where for the formula, it's okay. Because the goal of this course just want us to learn the analysis, not the physicals, Newton analysis. It's about physics. We will not relate so much physics, okay? Let's continue. As you can see for this example, the variable is y, the first derivative of y, the second derivative of y dot dot. In lecture 1 and 2, we have introduced some concepts for signal input-output system. And you have known the input-output system's equation. We should finally make it into x bar, ax. X is the variable, okay? Plus du. This is the result we want to get for input. And for output, we want to the formula y equal cx plus du. This is the form we want to get for input and output equation. Next, we would like to choose state variable. This one we call the state variable. The first step, okay? So how to choose the state variable? It's like the variable here is y, and it has two derivatives. The rule for choosing the state variable is if it has second derivative, then we just need to choose x1 and x2, these two variables. Why? Maybe you will ask why. Let's see in the following, okay? You should observe it again. Why we just need S1 and S2? Because if you observe it more clearly, you will find that we want to get S dot. What's that mean? The derivative is the final answer we want to have. So let's try what's the derivative of S1? It will y dot. What's the derivative of Y2? It will y dot dot. Okay, y dot. Include these three variables. No, the same variable, but with different derivatives, right? So this is the key. If you have n derivative, then the state variable you choose just need n minus 1. Okay? For this one, we need only one order, then the language order derivative. Let's see next. After we have choose the state variable and also do the derivative of them, what should we do? Okay, this is the second step I will show you. the thing we should do is that you should write out as start equal what? X plus BU. What's the B? What's the A? Okay, you should write it down. For Y, you should write what's the C? What's the D? Okay, this is what you should write down. But it's a metric. It always should be a metric, like S1 dot, S2 dot, Sn dot. But for this, always only one terms. For output, always one terms. So let's express S1 dot. It's easy to find S1 dot because you do the derivative, it will equal S2, right? So S2 equal S2. How about S2 dot? Maybe you will say equal Y dot dot, but not only equal Y dot dot, but also Y dot dot will equal, you can change the form. Y dot dot will equal minus KY minus CY dot over M. And Y dot will equal S1 dot, S2. So it will equal KY minus 2 KM, KM. And Y dot is equal S1 minus K over M. And here also have U, M, S1 minus C over M, S2 plus U over M. So this is the key thing you should do. You get this. Okay, we have two state variables. So we also find the two derivatives of state variables expression. Now we should express the output. Actually, output is also the easy one because output is equal as 1. This is the step 2. For step 3, we just rearrange the step 2 into metric. Then it's okay. So let's do a simplified assumption. It's that always when you analyzing a physical model, you should first have its input and output. You should first have its equation, right? After we get the equation, we first choose the state variables. The numbers the state variable we choose will depend on the derivative, the number of derivative. If it has n derivative, then the state variable we choose will become n minus 1, number n minus 1 derivative, state variable. This is the rule for the state 1, step 1. For step 2, we just need to rearrange them into inputs and outputs formula. For input formula, you should find that the state variable, the derivative of state variable, into this form. For output, the variable into this. For here, it will replace x, right? It will replace input, right? How could you express that like this way? This is the key point. And always, the method or the rule, after you see some practice, you will find that for the last one derivative of x, it will always rearrange by this equation, by the equilibrium formula. And for the first, not the last state variable, if it has S1, S2, S3, S4, like before the last variable, this three variable, you can always use this kind of situation. It's easy, it will be the easy one. And for output, you will always also use this equation when we do the derivative. So when you do the derivative, you should always write out this condition, because this condition will also help us to write out, to rearrange the input and output equation as the next step. And the third step for us is write them into metric, write them into algebra, using algebra to rearrange again. I think it will be simple, right? It also the use of this equation, right? It also the use of this equation. Okay, this is our first knowledge, state-space I/O relation. Sometimes, for mathematicals, you will see some models. Oh, not only the mathematicals, but also analyzing model. You should know the input you want to get output. So this method or this practice is used for something analyzing like this. Let's see. Here he gives us a counter example. Let's see what you want to express. It want to tell us, actually this counter example want to tell us, physical realization is not always possible. What does that mean? Maybe we could use mathematical to express them, but sometimes we should always relate it to the practical real world. But sometimes this kind of state-space I/O relationship, mathematical method, may not be able to describe the physical meaning, the physical realization of this model. Let's see counter example. The same model, mass spring damper, but the system would go this way to UT, and the system of mass would go this way in YT. YT would be the output expression for us. So the distance between them have a relative, should be a relative distance and a relative velocity. Finally, it is expressed like this. But as I have talked about you before, if you do not know this well, you can check it into dynamic subject or physics subject. Okay, but it's not the main point. The The main point is that you should know how to apply the state space IO relationship. So let's use the same equation, same method to see whether it is okay to use. Left side as usual, but right side has input derivative. So that we can do a physical realization. That's by anyway, S1 equal S-Y. So S1 dot will equal Y dot, S2 equal Y dot, so S2 dot will equal Y dot. The same way, right? But now we will find that the difference between the last equation and this equation is that the derivative not only come out for Y, but only come out for input. Not only come out for output, but also we have the derivative for input. So for this way, it's not very convenient for the method we just use. But actually, we will have our method to solve it in the next lecture. So don't worry about it. But you should know we will make some condition like this way. For next, we want to have a summary. If next time you see the models, like the first example we show, how would you do? The model's characteristic is that it only has the derivative of output and no derivative of input. This is input, this is output variable. Okay? So let's make a general form. The form of it we generalize like this one. And derivative of the output variable. And the coefficient of each one. Plus at the right hand side, it only has the output, input, no derivative. This is the first step. We should know, we should get the formula. For next, we should find how many state variable we need. It has n derivative, so we only need express until y to the n minus 1 derivative. As y equal y, as 2 equal y dot, as 3 equal y dot dot. So for as n minus 1 dot, we could use as n to express it. After that, we do the state variable because derivative because we want to know. Like before, as you can see, before n minus 1's x dot, you only need to use the equations, change that, this one. But for the last one, we will always use the equations to change its form. Also for y is the same. You only need this function, then you can get it. The fourth one, arrange them into metric algebraic form into this way: s dot equal as plus bu, y equals cs plus du, like this way. Okay. Also, always for inputs, we have one variable, so we only have one input. But for state variable, we will have n numbers n of state variable. So you have graphic, right? That's summary again. Sorry, I don't summary. Okay, next. Let's go to the next one. So what's the type we will introduce for canonical form and observed form? It's like when you calculate the state space variable, you will meet other situation. So these two forms are focused on solving the problems. This one. We just meet this problem just now. We have found that it has the derivative of output, or input of input. Sorry, it not only has the derivative of output, but also has the derivative of output. At this time, we could not express into this general form. So how could we express it? And these two are the methods. Actually, the main idea is make this without derivative, make the input without derivative. This is our method. So what would you do? Okay, let's start from the most general input and output realization. Note that input as slightest order is u. Otherwise, we violate causality. As you can see, the form, we want to make it a realization. The canonical form he used. Let's see the derivative first. Let's use the dither operator. So what's the dither operator? I just introduced simply. Actually, it's just an expression to express the derivative. How do we express y dot? We will use dy. So d means one derivative. What is y dot using the operator? It will d square y. How about y dot equal d3y? So this is what the d operator means. It's just an expression to express the derivative. Okay, let's use the d operator like this way. We just introduce it. Next, we change this equation into this equation using the variable. How? Y to the n derivative, change it into d to the n y. The same way to represent it. Also the same way for u to the n derivative into d to the n derivative become u. The one derivative of u is become d times u. Okay? So now we have eliminated the derivative of it. What would you do next? We can take it out, take y out. We can take u out, take u out. So you can get this one. These are the coefficient before y. These are the coefficient before u. We want to make it more simplest. So we use AD and BD to express it, okay? We also define all of them equal PT. So we can define PT equal AD times YT times output, and the coefficient times input. Now, we want to make it simple. How could we make it simple? Because as you can imagine that now here do not have a derivative. This part do not have a derivative. This part do not have a derivative. But what we want to like actually, we would like here have a derivative, but here have no derivative. So it achieves its purpose, but it do not achieve. So we should change it into having derivative. We should change the output having derivative. So how? How can we do? Let's look at here. Take the output into this way and define zt equal ut over ad. This one is defined as zt. So finally, sorry, it's not like this way. Sorry, cut what I said before. Actually, it defines yt over bd. This one is zt. So ut will equal ad times zt. And ad you know, right? Zt, ut. You have invented an intermediate operation zt. And in the last step, we have regained physical meaning. Finally, you could find these are the new form we created. For the left-hand side, we create a new output with derivative. Z to the n derivative, Z to the n minus 1, Z to the second derivative, Z to the 1, Z to the 0. And for the right-hand side, we only have the non-derivative of input. These are the probability results we want to get. So you may be confused about how it gets. What's the logic of it? Is that you should know what you want to do for here, right? The problems you want to solve is make yt with n derivative. Make ut with non-derivative. The logic is that first we do the operator method. We achieve this goal, right, using the operator. But this one do not achieve. So how? How could we do? Then we can use the operator back. Okay. Or we could also say we take BD because AD times Y over BD. By this way, for the right hand, U will have a non-derivative. But how could we rearrange this? We create a new output. This means ZT. Then the total one, you can write it AD times ZT equal U. This is correct. Right? So the logic is just using the D operation and rearrange it. Okay, rearrange it. Next, let's do next. You can come back to this method. It would be the same. Just take a space variable. Find how many derivatives have first. Second, try to write them into input and output form. And the third one, write them into metric form. Finally, the form would be this one. The input, this is for the output. Okay, it is the same. And after that, we will have some practical form. You should remember it, and you should first realize it, understand it. After that, you remember it, you apply it. Let's see one example. We just use the example, this one. We have the formula of this. You observe it, you have the derivative for input. So you can use canonical form or observed form we will learn next step. For canonical form, you try to find out the variable we need. Like we need B0, A0, BM, B1, A1, BM, BM. We need minus A0, minus A1, minus N minus 1. So what are they? They are the coefficient between this one, right? Don't be worried about it. You just apply it. So first, I have second derivative. So we choose two variables. AO should be the coefficient for y to the 0 derivative, this one. A1 should be the first derivative of output variable, its coefficient, so this one. And for B0, it represents the coefficient for input with 0 derivative. This one is this one. And for B2, we do not have, so we Bn equals 0. Let's write the state variable if we do have a physical meaning of S. Express it. For this form, you only have 2. S1 and S2, right? For S1, it will equal Y. S2, it will equal Y dot. These two, you know. these two, just write them in two. And as you can see, the real one will be this one, but before B2 is 0, it's only B2, B0 and B1. For you, the match of it is the last one will be 1. So here, he write 0, 1. But the first one will be 0. We should see the right output. En, it should be B2, n equal 2. But B2 is 0, so we write B0. After that, we can write this metric into here. Comments on the meaning of the state variable, discuss and hint, not a full explanation. We have the derivative it before, AD. AD is the coefficient of input for the first beginning of the equation. We know S1 equals Z, S2 equals Z. So, using the D operation, you can get this one. So there is some imaginary signal we will obtain if we use the square MCK. If we use the same MCK, but the output as a force instead of a displacement. The last equation has the same structure of a system with force as the input. After introducing it, let's introduce type 2 of the form. The conclusion for a specific form, we will not show derivative here because the derivative is a little complex. Let's just show you the conclusion. And next, we will try to make it application. Let's see some example. Original, LT, mean discrete system, okay? We also need to express it into this metric form. If I use this variable as prime to x, related to x, by a linear combination, s equal transpose. What's this mean? This is the relationship between the new variable and the original variable. S prime represents the new variable, S represents the new original variable. Where T constant metric and transformation metric is non-singular. If they are opposite, if we want to change the old variable into new variable, we can use this method. So we want to write the state equation using the old variable, new variable, sorry, for the same system, U and Y are the same, but A prime, B prime, C prime, D prime will be the new matrices. Now let's find the relationships between the new and the old. The old variable we express like this, so it also do the transpose like this. After that, he gets, because this one is the T times S, so he also take it into this one. After that, for B, so finally, for C also, T S prime, right? Okay. T S prime will also equal S. And CT will also equal C prime. The new matrix is defined as this way. Maybe it's a little difficult or not very clear to use it, but let's see the example for the same way. Assume we have a variable V1, V2, and the output Q. We can express them. We can express them as this one. If we want to, but this is the norm, okay? This is the norm. This is not a keyword, but we want to show you the transformation from the original to the new one. So let's choose as one dot. The new one will equal this one. So using the transpose one, using the formula we calculated out before, then we can get all the variable we would like to know. A prime is diagonal. A don't have this property, which means it uncoupled the system. Each state equation is only function of one state variable. In practical terms, this approach gives us a better understanding of the system dynamics.